Hey class, it's Professor Rourke. So I wanted to make a little video about 4.8, which is about Newton's method. And unfortunately, in the fall, when we're short class time, it often gets kind of pushed to the side. But it's a pretty short section, and it can be really cool, some cool applications, and it really just takes some little bit of using your calculator effectively. You don't need to use your graphing calculator, but it can definitely make just the calculations a little bit more helpful. So what I wanted to do is I wanted to go ahead and take a look at our online textbook just so you could see um, where I'm going to pull some of these problems, and then I thought we could work through some examples together. Okay, so first things first, this is your WebAssign course page, and I just wanted to make sure you could go to your ebooks and just take a look that way. I know there's lots of different ways to get to it, but especially for the online textbook, I feel like it's really easy to forget that it's even there. So I'm going to go ahead and navigate to chapter 4, and again, I'm going to go then to section 4.8, okay, which is all about Newton's method. Just to kind of take a look, and then again, I'm going to show you how we can use our graphing calculator to make things a little bit easier. Okay, so the whole idea is that there are some equations that we literally cannot solve, right? We can solve quadratics, right? We can solve some other polynomials if we're kind of lucky. We can solve some logarithmic equations, right? Exponential, but there's some that we literally just either can't solve or it would just take so much time, it's not even worth it, right? And so what our main man Newton discovered, which he is a smart dude, is that let's say for instance we had some equation f of x and we want to determine the x-intercept, kind of like what they have in figure 2 on your textbook, right? And so the blue graph is f of x and r is supposed to be this x-intercept, and we can't solve for it. We don't have a way to solve for it. We could guess, right? We could be like, well, it's between here and here, but like how close, it's hard to say. We could maybe get accurate to 1 decimal, maybe 2, but more than that, probably not. So Newton discovered this way that we can actually use the equations of tangent lines to get better and better estimates. There are a couple of times it doesn't work. Like for instance, if the derivative equals 0 anywhere close by there, you can kind of see it's not going to work out. It would the tangent line would shoot off away from where we're looking. Okay, so for instance, what we have here again is this. We're trying to estimate this x-intercept r. And so first we pick just a point close by. They call that x1. And then they find the equation of tangent line at x1. And then what actually happens is wherever that tangent line intercepts the x-axis, that is our new x2. Okay, and so then the process is going to repeat. This time we're going to find the equation of the tangent line at x2 right here, right? And so you can kind of even sort of get an idea just from looking here. They're like, okay, it looks like maybe if I drew a tangent line through here, which again, this is just going to be real dicey, I am getting closer, right, to the x-intercept. And then we would call this point where it intercepts the x-axis x3, right? And then we could do this again, and we could keep doing this over and over until we got closer and closer and closer. And it's like, well, how do you know if you're closer or not? Well, the decimals won't repeat after a while, right? Or they'll maybe tell us to go to a certain level of accuracy, in which case we'll check that too. Okay, so that's just kind of a very brief overview. Again, if you want to take a look at your textbook, there's also some good videos out there that just kind of explain the idea of Newton's method and how he, again, figured out that if we find a point close by and then we find where that tangent line intersects the x-axis. And so that's what they did have here. They replaced for the equation of the tangent line, they said, okay, we want to figure out where the tangent line crosses the x-axis, and then we solve for x2. And so in this little equation, you can see what they have to get the next iteration. So if you start at x1, x2, you can get by a little bit of simplification, nothing even that complicated. It would be the first iteration x1 minus f of x1 divided by the derivative at f of x1. Okay, so essentially this is the main formula that we use for Newton's method. And then once you get x2, you could then use x2 to plug that back in and find x3. And so you could say x2 minus f of x2 divided by the derivative at f of x2. And then you could do that forever, right? So this formula here is technically the formula for Newton's method, and it's saying however you want to find the next one. So x of n plus 1. So wherever you're at, the next one you can find by taking current one, x of n, minus f of x of n divided by the derivative of f at x of n. So like in my mind, I think about it like to find the second one, you take x1, whatever your first x value is, minus f of that at that x value divided by the derivative of f at that first x value that you pick. Okay, and so again, there's just the graphs here just kind of show how we can get closer and closer and closer. And then it says, okay, if we did this forever, we would get to R, right? So they talk a little bit about how Newton's method can kind of fail. Again, if the derivative is like close to 0, they kind of show this figure, how if the derivative is close to 0 around a solution, the tangent line's not going to intersect closer to the x-intercept. And then, we have this nice guy with his little video. But I wanted to show you how we could do this, especially in our graphing calculator for the more complicated ones. There's this little explore it, which is great and all. But let's see if I can find a good one. I like this one. This one's nice and ugly. Okay, so this is example 3. It says find correct to 6 decimal places the solution of cosine x equals x. Okay, so you can take a second to think about like how would you even solve for that, right? Like there's no like, no, I can't. No, it's gross. So instead, we can use Newton's method to help us out. So just to make sure we're on the same page, first things first, we take this equation. Newton's method is set that it's like we have f of x. So you want to set this equal to 0 and call that f of x. So the textbook subtracted x from each side, so we can do that too. Or you could go the other way and you could say x minus cosine x. It doesn't matter. We're going to get the same solution either way. Okay, so I'll stay consistent with the textbook. I'm just writing down what the textbook says on the right-hand side. And then again, the only other thing we need for Newton's method is just the derivative, which is again, really the great thing about it. So the derivative of cosine x is negative sine x minus 1. And so then each time we want to use Newton's method, we're going to follow this pattern, which remember again says in order to get like the next one, right? Whatever the next one is, you start with your first one or the one you're on, and then it's going to be minus the original function divided by the derivative. Okay, so I'll say cosine of x of n minus x of n all divided by negative sine x of n minus 1. And so then it just becomes a matter of like crunching the numbers over and over again. Sometimes for these problems, they're going to give you an initial value to start with, and other times they don't, okay? So this one I don't think does, right? No, it doesn't really give us anywhere to start, but like you could sort of just look at the graph maybe of where cosine x and x intercept, or you could set cosine x minus 1 equal to 0 and just get like a rough starting value, because the whole point is that as long as you're somewhere close and the derivative isn't equal to 0 somewhere near there, you're going to get to you're going to be able to get closer and closer. Okay, so for instance, I went ahead and opened up my graphing calculator on the computer. Not gonna lie, sometimes it freezes, so bear with me if it does that. But I could go ahead, let's clear out this other stuff in here, but I could go ahead and enter in, again, the cosine x minus x, that original function, in order just to get like a rough, very rough first estimate value. Or if it's like a graph that you already kind of know something about, you might feel comfortable to kind of pick your own guess without thinking about the graph. But I'm going to do zoom trig, I'm sorry, because I feel like sometimes that helps me out a little bit. Yeah, that looks pretty good. And so it looks like here you can like trace over if you want to, but it looks like it's like, somewhere between 0 and 1, we could say. So you could pick any number you want between 0 and 1 to start out with as your initial guess. The textbook picked 1, so we can do that. But I'll go ahead and pick a different one just to kind of show you what it would look like. Sometimes if you pick a better initial guess, maybe we might get converge faster, right? But it's all like, you can sort of pick wherever you want. So they started at 1. Let's go ahead and start a different one just to kind of see the little difference. I'm going to start at zero point 0.5. Okay. And what I'm really going to be do to get the second term, just a little reminder, I'm going to take 0 0.5, right? And then I'm going to subtract away cosine of zero point 0.5 minus zero point 0.5. That's just the original function evaluated at zero point 0.5. This just number I just picked. The textbook used 1. So either way, it's all good. Okay, we'll see how they kind of compare. And then we use the calculator to get us an estimate. But I wanted to show you again how we can make it really quite simple. We can go to our graphing calculator. I'm going to go to y equals, and I know I just graphed the original function just to kind of get a good starting value, but we can put in essentially this whole expression. Okay, so we can put in x minus, and it'll always kind of look like that because that's always the formula. It's always x minus the original function divided by the derivative. So I'm going to type in the original function. So I have x minus parentheses cosine x minus x, right? And then divided by the derivative, which again we said was negative sine x minus 1, right? Yeah. Okay, and then I'm going to close those parentheses. So all I did again was I just entered in essentially like the formula for Newton's method into y equals. And the reason I did that is so I can just get some quick calculations. So for instance, the first one that I wanted to start out with was 0.5, right? So this is what I like to do. I think this is the easiest, but there's a lot of ways to do this. I could just go to my calculator and put in 0.5 minus cosine of 0.5 minus 0.5, all divided by negative sine of 0.5 minus 1. And get that number and then do it again. But it's just a lot. So this is what I like to do. I like to start out by entering in my initial value and just to the main calculator screen. So I'm just going to put 0.5 and select enter. Which again, I'm like, why would you do that? But I'll show you hopefully why. And then again, there's a few ways, but this is, I think, the easiest. So first, you type your first entry in, put 0.5. And then what I'm going to do is I'm going to recall y1 because that's where I have my entire equation. And I'm going to evaluate this at 0.5. So you might remember back in the day, we can recall y1 a few different ways. The old school way, which is what I always remember, which they've made some improvements because I know it's a little clunky to do this. But we can go to vars and we go over to yvars and then we push enter on function and we push enter again on y1. And I can show you another way because we're going to do this a bunch of times. And then I want to put parentheses. I want to evaluate it at 0.5. And so this is why I put 0.5 in first, is so that I can then just click to recall that. You can hit second and then you can hit the negative sign. Okay, and so what this means is it's going to take y1 and then it's going to substitute in 0.5. Which is why, again, I put 0.5 and I pushed enter because that is what they think of as like the answer, is the whatever is right, the output right above it. Okay, so I'll show you hopefully why again that will help us at some point in time. And then you just go ahead and click enter. So this means my second iteration estimate is this lovely thing. And again, here it told us to go accurate to 6 decimal places. So what that means is for the 6 numbers, we could stop when the 6 numbers are the same. Okay, because then that is telling us that essentially we're as accurate as we need to be. We could keep doing this over and over again if we wanted to try to get more accurate, but all they want is to 6 decimals. I mean, 6 decimals is pretty good, right? So my second iteration again is 0.755222. So you'll see the textbook, they started out again at 1, and their second iteration was 0.75036,387. So we're both pretty close, no matter which iterate what we started out with. Our second iteration is pretty close. Okay, and then we just do it again. So we want to take now this x2 value, and then that is going to be going in for x. And so the reason I like to do this is it's real simple, because all I need to do now is just recall the exact same thing I just put in. Because if I do y1 of answer, it's going to take this 0.75522,417 and it's going to put it in to y1. So there's a few ways you can do this. You can arrow key up if you want to y1 answer. Some of the older calculators you can't scroll up. And so what I used to do back in the day was I would hit second and then entry. And that just recalls your last entry, which is exactly what we want. We want to have evaluate y1 at the second iteration. Okay, and so then we just can click enter, and it's like that fast. It's that simple. Okay, so what I would just jot down is that my third estimate is this lovely guy. If I can write on here, I don't know if it'll let me. Um, come on, come on. Let's see. I don't know why it won't let me write on it. That's okay. Okay, this is my second iteration, which is, I'm sorry, technically x sub 3, because that's 0.739141661. And then we could do it again to get technically my fourth iteration. And I'm going to keep doing this until, again, I have the first 6 decimals correct. So if you want to, you can scroll up if you have like a newer calculator and just push enter. That will bring up y1 sub answer. So now I have 0.739085139. So I can do it again this time just to show you that there's a lot of ways to recall your entry. I'll just hit second enter. That's how we can recall the entry. And now they are getting pretty close, 0.739085. Yeah, I think, yeah, they're accurate to 6 decimal places, because that's all they asked us to do. 1, 2, 3, 4, 5, 6, they're the exact same. So what I would say is that the answer to this solution, this function, up to 6 decimals is 0.739085. Okay, and you can see I technically got there, I think, in 4 iterations, and the textbook, when they started at 1, they had to go 5, but I mean, they're pretty close depending on it. So again, sometimes you can pick a better estimate to start out with, but as long as it's not near where the derivative is 0, you'll get there eventually. And especially when it's so quick and easy, and the calculator, like a little bit extra time won't hurt, right? Let's go ahead and try one more, just so we can get an idea, because I know some of us, again, are feeling very comfortable with the calculators, others not so much. So let's go ahead and clear that out and take a look at another one of the examples from the textbook. So these are examples that you could definitely have in WebAssign. And so, you're always more than welcome to take a look at these. And just to kind of get an idea. So let's see, this one says, let's look at number 8 here. It says, use Newton's method with the specified initial approximation x1 to find x sub 3. Actually, I could do that, but I want to go a little harder. I want to find a harder one. This one, I like this one. This one's good. This one says, first, explain how we know that the given equation must have a solution in the given interval. Okay, and so when they say that, really what they want you to do is they want you to use intermediate value theorem, where you can plug in essentially 3, and you can, I'm looking at for number 14 right now. It says negative 2x to the 5th plus 9x to the 4th minus 7x cubed minus 11x equals 0. And they give you the interval 3 to 4. I can plug in 3, and then I can plug in 4, and they should be opposite signs. So using the intermediate value theorem, that tells me that somewhere in there it has to equal 0, right? But I wanted to make sure I showed you just another way, one more time, to give you how we're going to use this in the graphing calculator. They also don't give us here initial start, but it does help us a little bit more, because it just says between 3 and 4, right? So whatever your initial guess is, it's somewhere between 3 and 4. I often will pick 3.5. I feel like it just makes sense. You know what I mean? But I'll say like x of 1 equals 3.5, maybe just to get the ball rolling. And then remember, all we do for x sub 2 is we take whatever x sub 1 is minus the function at x sub 1 divided by the derivative. So all we really need that we don't have right now is the derivative, and then we can go ahead and put this in our calculators. So let's see here. The derivative would be negative 10x to the fourth plus 36x cubed minus 21x squared minus 11. Okay, so when I go to my calculator and when I go to y equals, okay, I'm going to type in my whole shebang here. I'm going to put in x minus the original, which now I have some regrets that I picked this one because it's going to be kind of annoying to put into the calculator, but still less annoying than actually doing it. Okay, minus 11x and then all divided by the derivative, which again was negative 10 x to the fourth plus 36x cubed minus 21x squared minus 11. Okay. Whew. All right, so let's go ahead and get the graphing calculator out, and just so I can show you one more time how easy it is to do in the calculator. So if we go to y equals, and I'm going to type in exactly what I just wrote down. I'll just go ahead and clear out my last one. So it's x minus, and then I'll put some parentheses, negative 2x to the fifth plus 9x to the fourth minus 7x cubed minus 11x. That was the original, right? So I'll double check to make sure that is the original. Yes, okay. And then divided by, in parentheses, what we had for the derivative, which again was negative 10x to the fourth. Whoops, I missed an x there. I want to make sure I get that. Okay, negative 10x to the fourth plus 36x cubed minus 21x squared minus 11. Okay, I was still on the exponent for that last one. So close, so close. So let me make sure I have that in there correct. Okay, no, I don't want a box up there. Go away, minus 11. Okay, sorry, I'm just talking to my calculator kind of aggressively. All right, so you can always like scan through, make sure you're looking okay. If you want to, again, you could always have graphed the original function just to make sure, right, you're on the same page. But essentially, this graph isn't what we're looking for. This is the whole Newton's equation, Newton's method formula. And so that's not the original. All right, let me go ahead and clear all this stuff out. And remember, again, this is just what I like to do because I'm extra lazy, is I like to actually type in 3.5 to get things started. This is just my extra lazy way of that. Literally, after I do this, that's the output. I can just constantly recall the last entry and not have to change anything. So just my lazy methods here. Okay, so now I'm going to recall Y1. So I showed you the longer way before where you went to VARS. Some of the newer calculators, I believe, if you hit alpha trace, it'll pop up your equations, and so you can recall Y1. It's a little quicker. That was sort of a newer addition, I think, because going to VARS, Y1 is a little clunky. This is a little less clunky. Okay, and so we want Y1, and I'm going to go ahead. This is why I put in 3.5 to start out with, is so that I can hit second answer, because now the answer is really like whatever the output was before, and now every time I do this, whatever the answer is for that next iteration, I just go ahead and if you hit recall the entry, it'll just keep putting that in, right? Okay, so if you have computer science major, you probably have a better way of explaining what I'm talking about, but also, I don't know, maybe, we'll see. Okay, so, all right, so my second X2, my second iteration, I remember I started with 3.5. You could have started with anything between 3 and 4, would be 3.3291736. And it says again to accurate to 6 decimal places. So I want to repeat this again to see what X3 would be. And then the beauty of this is I don't need to really type anything else in. If I just recall the entry by hitting second enter, it'll recall exactly what we just did. but instead of plugging in 3.5, it plugs in 3.3291736. Okay, I'm just very lazy. I don't really feel like typing those numbers in. I didn't even really want to type those equations in. So I don't want to type that, especially more than once. All right, so this would be 3.2787, I'll say 065. Those don't match past, like, they don't match really at all. So that tells me I got to do it again. Okay. And then, so again, I'll just hit second enter to recall. And then I get 3.274. So some of more is matching. So yay, that's good. But still not to the 6 decimal place. So we got to keep going. 7450 0.6. I'll leave it at. Okay, and then you would just keep doing this. If this was like a graded paper, you would just make sure that you would, oh, sorry, I don't want just the answer. I want to do the whole entry. You would want to just make sure that you kept recording your answers until, again, it was 6 decimal place accuracy. So 1, 2, nope, not there yet. You could also, if you want to, just arrow key up to recall the whole entry. Woo, it's looking, oh, that's looking pretty good. I think we got there because it's 3.274472663. All of those numbers were the same, and again, it's into 6 decimal places. 1, 2, 3, 4, 5, 6. We are there. So technically, the answer to this equation, the one between 3 and 4, because it's polynomial, so it's probably more than one, is 3.274472637. Okay, Newton, you crazy dog, you. Okay, so I hope this was helpful. Again, Newton's method is pretty short overall. It's really just the formula, and then looking at some of the ways that we can apply it. And I think the best use of your time would just kind of be getting comfortable with the quick calculator steps of how we can crunch these numbers out really quick. Okay, so I hope this is helpful. Again, we're going to count this as bonus points for this semester, but if you're watching this later in the future, not in fall 2024, it might not be a bonus, so I'm not sure. We'll see. But thank you guys. Please let me know whatever questions you have. I picked, again, 3.5 to start out with, but if you picked something other than 3.5 and maybe you got there faster, maybe just, let me know. Sometimes there's you can even do a race to see who gets there faster, get really crazy. All right, thank you guys. Please let me know however I can help again. All right, take care. I'll see ya.